All right, welcome back everyone. So today we're continuing our exploration of the topic of entropy. And remember that we had previously discussed that for a cycle, I'm not going to draw another phase diagram, but we're talking about a cycle where the state of our system moves between different points on a phase diagram, but always goes around and comes back, ending at the same point that it started at. It can go any direction around, it can go around to any points. It's just a cycle. If at some point it returns back to where it has started. And we've talked about how for a cycle going all the way around, entropy always increases. So, having that as our foundation, we're going to explore some of the different ways that we can write this general equation for the entropy total of a cycle. So, delta S, that's our change of entropy, and I'm going to do subscript total cycle. All right. This can be split into two pieces. Going around the cycle one direction and then coming back in another direction. So here's what I mean. It can be split into delta S total, let's call this forward, all right? Now we don't care what direction forward is. And backward. So this is telling us something not too profound. Let me actually change my mind. I'll throw a real quick PV diagram up here. It's not going to have axis labels, all right? I'm just going to have some points like this, and we can say that our system goes from here to here, and then here to here. And let's call that the forward part of the journey, right? There's some entropy change on that part. And then coming back, either you could come back down here, or you could turn right back around and come back here. We would expect that by the time you get back, that total entropy changes the same, because you're back to where you started entropy-wise, okay? Well, as we're gonna see, we're back to the same place state-wise, okay? We're back at the same state, but as we're gonna see, there's entropy generated. Now that's guaranteed by the second law. I want you that to be ringing in your ears this whole time. As you see this, you're like, okay, well, the second law tells me, the modern physics expression, which is the simplest, if I go in a cycle, then entropy increases. That means that my delta S for the total cycle right here, this has to be greater than 0. Okay, for any real system, it's greater than 0. And I'll review real quick right now that in the case where it's equal to 0, well, that's my case of having a perfect system. Okay, if everything is perfect and theoretical, then I can have it equal to 0. It can never be less than 0. Okay, and in the real world, it can never even be equal. So in the real world, it's always greater. All right. So where does that come into play here? Well, both going forward and going backwards, there's some entropy being generated. That makes sense. But what people like to do, and it becomes very useful to, is to split each one of these into the perfect part and then the generated part. Because remember, in the perfect cycle, there's no entropy generated. So let's, instead of calling it one thing, the total, let's divide it out. Here's what I mean. Delta S total cycle, I can write this as delta S perfect in the forward direction plus delta S perfect in the backward direction plus some entropy that's generated. Okay? So check this out. I've split, and this is obviously two pieces. Some of the generated entropy comes from the forward, and some of it comes from the backward. Okay, but there's some amount that's total that's all generated, and then these are the perfect pieces. Okay? So notice that here we had, and I don't know where to fit this in. Here, this forward and backward, we're going to have one of these be positive and one of these numbers be negative. But because the total cycle is greater than 0 or positive, these always need to add to a positive number. And so the larger value is positive. Okay? So let me give you a couple examples of what we had up here. Okay? We could have, if we had a total cycle entropy, you know what, I'm going to erase this line and do the examples below, and then we'll come back to that. If we had a total cycle entropy of 5, let's say, then maybe we could have a forward entropy of, I don't know what my example was, it can be any number. I had made up the example of 27. And then my backwards entropy is going to be, it's going to be a negative number, right? One of these numbers is positive, one of these numbers is negative. And if you want to make it look like this formula, I can do a plus in the middle and a minus 22. Okay, this delta S can be positive or negative, so one of them has to be negative. But you'll see that the total is always positive because that side is greater than 0. Another way that I could do this, just to show you that we don't care which direction we call forward and backward, I'm just using the words forward and backward to mean one way and the other way. That's all I mean. So we could have the forward direction be the negative one. If I wanted to get 5, I could also have this be negative 20 and this be plus 25. Okay, so the forward, I mean, one of these is negative, one is positive. It doesn't matter which. Here are the things that matter. The larger one of the two is always positive. In this case, the larger one is the positive number, so that we get a positive. So this is an example of what I mean, and of course all the units of these are joules per Kelvin. Okay, that's the units. So now let me erase this diagram and let me write up the equation that I had down there. So we had split this out, total cycle into the perfect parts, perfect forward plus delta S perfect backward plus the entropy that's generated. Okay? So if I was going to run some numbers, oh, by the way, in general, all right, now this was these two guys, one positive, one negative. We have the same deal. One is positive, one is negative, but they're of the same exact magnitude. So what I mean is that the perfect cycle, as we've discussed, is the same forward and backward. So the perfect components of these are the same values. They cancel out to 0. So if I had my example of 5 over here, this time it's like I'll use 22 again, 22 in the forward direction and negative 22 in the backward direction, and then plus 5. So this one is in some ways more useful than that one. That one was just you add up two numbers, one of them is bigger. This one says, let's break this down. There's always these forward and backward components that are exactly the opposite of each other, so they cancel. They have the same magnitude. So this total part is always equal to 0. And then this over here is just the generated part in the cycle, which is the same answer as we have over here. Okay? So I'll write up my final example and then hit the punch line. This could be negative 20, and this could be positive 20. And then plus 5. So here, the generated part is always going to be what's that side. So the punchline from this is that, oh, I didn't even write the S here. I'm sorry, this is delta S, total cycle. Delta S total cycle is equal to S generated. I hope this is obvious to you why that's the case. All right, this is like the second law of thermodynamics, right? This generated entropy is always positive, so this total cycle entropy is always positive. The change is positive, meaning it's always increased. Because these two parts, the perfect parts, they cancel each other out. Okay. I had a note here. I just want to make a couple notes. Right here, this was like taking the cycle and dividing it into one-way trips. Okay, that's essentially what we're doing, dividing it in one direction of the cycle and then the other direction of the cycle, going back. What else? Oh, notice that when we're talking about these perfect entropies being transferred, that we'd only discuss that when there's energy being transferred, only heat gives off entropy. And this went way back to our intuitions about, okay, work can be perfectly converted into heat, but heat can't be perfectly converted into work. That helped us even set up what the heck entropy is. So just remember as a note, work doesn't transfer entropy. So we want to remember that fact. And then another note on how to write this is that what I'm calling perfect right here, wherever you see the word perfect, there's another term for it. And that term is reversible. So if you see, the book calls it this. The book calls it delta S reversible. The word perfect is easier to understand, but it's easy to see why these are the same, because obviously in the case of reversible, that's what we mean by perfect. Okay? If something is totally reversible, it cancels out. There's no entropy generated. So it's a perfect cycle. Okay. So now I want to, this whole board is for a cycle. But since we've taken the cycle equation and we've chopped it into its constituent pieces, we notice that we can also write this one way. So now I'm just going to do delta S total, and I'm not going to denote that this is a total cycle entropy. I'm just going to say, even if there's a process that just goes one way, and we don't want to study it coming back, we just want to study it going one way. Delta S total entropy is equal to delta S one way. So this is exactly like I wrote forward or backward. I don't know what you want to call it, forward or backward. I'll just denote it one way, but it's the perfect or reversible entropy plus the entropy generated. Okay, so this split out of dividing the reversible from the generated or the irreversible, that can be done even if you're not talking about a cycle, even if you're doing it one way. Now, where would this entropy come from? Like, if we're talking about something that goes one way, where would we get entropy? Well, it's generated in the cycle by something transferring across the system boundary, right? So we've got a system, and we've discussed that there are two ways for this will be an open system in the most general case. This is energy and this is mass. So energy flow and mass flow. But then within energy flow, we have heat and work. And remember that work doesn't contribute. So this thing right here, this term, is entropy flow from heat or mass flow. Because mass has entropy, right? It's randomness in a system, so this marker carries with it entropy. If I cross the system boundary into the system with this mass, it's increasing in entropy. And of course, heat is the main thing we've talked about for our formula for calculating entropy. So this is entropy flow from heat or mass, okay, that goes in, and then this is the generated entropy. The last comment on this section here is that you notice that we can write this equation in terms of a dot form. So where do I want to write this? I guess down here. Delta S total dot, which you can see in a minute. This is one way perfect dot plus S dot generated. So I've taken this equation and I've written it in dot form, means dividing every term by a factor of time to find the rate of entropy flow. And then there's something called a steady state system. And in a steady state system, what we mean is that this side of the equation goes to 0. That is one way to even define a steady state system. So the total entropy out of everything, there's no entropy being lost or gained total. So what we have is that if that's 0, then we can move 1 to the other side, and we get the delta S one way. The perfect entropy generation equals, I should call it entropy generation, the perfect entropy flow, or the reversible entropy flow, equals the entropy flow generated. Okay, so this is a useful equation if we have a steady state system to calculate the generated entropy. Let's see what, and there's a minus sign, because we moved that to the other side of the equation. So negative. Let's see. I think that's all the comments I have on that. So let's talk about the divided board here. Knowing this, there's also one more way to divide the system, divide the entropy equation up, and we could always say that delta S total, right? We could even break this down even more if we wanted. That has to account for the entropy change of the system and the surroundings. So that's sort of an obvious fact. I just want to write it because sometimes you'll see that equation written out too. The actual system that we're dealing with could have its entropy change, but also like the air around it that's just outside of the system boundary within the immediate vicinity, that can also have an entropy change. So a lot of times you have to calculate both when we're looking at entropy total. And we did this in our experiment that we did last lab with the flywheel machine that drew heat from the coffee cup. We had two terms, and I put them up on the board, but you notice that there were two things there, two terms that you had to add up, because the second one was the surroundings. So we needed to include both of them. So let's actually talk about that experiment. So our flywheel experiment. So what was up with that, especially that last question? Well, now, looking at what we've discussed, you should be able to answer that last question of can we actually find the entropy, the value of entropy generated? And surprisingly, the answer was no. Well, let's go over why we can't do that. We have the delta S total equals delta S forward, perfect. I'm going to call it forward. You could call it one way or whatever, plus the entropy generated. Now, I've not written the backward in here. And this is an interesting thing that we didn't get into on Friday, but I tried to explain a little bit in answering that final question. Notice that we never did the reverse of what we did on Friday. What we did was we had a coffee cup that started at a high temperature and it went down to a low temperature, and that change in heat we extracted out using our heat to work machine by doing some work. But what we never did is the opposite. We never were able to take that heat lost to the surroundings and put all that energy in the form of heat back into the coffee cup, and we, instead of extracting work, we would have to dump in work to do that. That's guaranteed by one of the statements of the second law of thermodynamics. And then our temperature of our coffee cup, or the water in our coffee cup, would actually increase because energy is being dumped back into it. That is what would have been the reverse. So that experiment was not a complete cycle. All we did is went one way, or went forward. So I'm not writing this as the total cycle because that's not what we did. We only went one way. So we could calculate the perfect reversible entropy generated, or entropy in the system that was in the form of heat flow. And then we also have the entropy generated, okay? And I think we calculated this, oh, and this side had two terms, remember, just like we did up here, the total can be broken down into the system plus the surroundings. And I'll just rewrite this side real quick. Forward, perfect, plus S generated. Okay, so these were the two terms that we calculated, and we got a number. I don't remember what that is, but I'm thinking it was about 9. So 9 joules per Kelvin of entropy was what the number we got was. And the question is, can we find the entropy generated? Well, no, we can't. Because 9, well, it could be, I've written down a bunch of silly examples, but we could have 3 units here of the reversible entropy, and we could have 6 units of generated. Or maybe we have 2 units of reversible and 7 units of entropy generated. Or maybe it's the other way around. We could still have these same 2 numbers, but this is an even different case, where we have 7 units that are from the perfect part of the process and 2 that are generated. And you're like, maybe I'm still not understanding this. Here's one way to think of it. If we had a machine that could do the process we did on Friday in reverse, if it could do it backwards, this amount of entropy here, we would get back. This we would never get back. That's one way to think about it. This perfect entropy generated would be canceled out by doing the cycle back. So if it was 3, then when we went to do the cycle back, we would get -3 to cancel. But our generated would be 6. Whereas if it was 2, then our cycle back would give us -2, that would cancel, and our generated would be 7. So this number is what we can get back just by reversing it, and this number is how much we cannot get back. This is our second law entropy, or our entropy that's always increasing, okay? And because we have this, the technical term is degeneracy, which means that there's multiple answers that could all fit our measurement, we cannot actually know that generated quantity. So that's kind of a conundrum. What we need to do is this reversible part right here. We need to somehow isolate only that. So let me make a note of that. Isolate only the reversible part. Now, if we could do that, we could solve this problem. If we could measure 9 and then we had a way that we could measure this number and say, aha, we got 7. Then we could get that generated entropy of 2. Turns out that on the next board, we're going to talk about how this is done. So if you wanted to isolate out the entropy of a cycle, the reversible entropy of a cycle, then all you would need to do is have the cycle be perfect and measure that, right? Because with a perfect cycle, let me remind you, in a perfect cycle, the entropy generated equals 0. That's what defines a perfect cycle. So that means that our total number, when we do the cycle and we measure it, well, that is what the perfect or reversible entropy is. There's none lost. There's no generated entropy. So we need to, I'll write it here. Measure the entropy of a perfect cycle. Obviously, in the real world, this can't be done. It cannot be built. There's no way to ever build a completely perfect cycle. You can build them close, but not exact. Hopefully, we're all good with that. But there was a physicist, a famous man studying thermodynamics by the name of Carnot, and he was one of the first guys to invent a way of making a theoretically perfect cycle. And so the cycle's named after him. It's called a Carnot cycle. And this is an important term, so I'm going to box it up. So a Carnot cycle, let me define it for you, is a theoretical perfect, or I'll use the exact word, reversible. This is perfectly reversible cycle. And we're gonna do an entire lecture in a week or two on the Carnot cycle and explain what it actually is. Like, we can draw pictures of like a piston, compression, and stuff like that. But at this point, the exact details of what a Carnot cycle are don't matter. Remember that we have not yet delved into the details of any of these cycles, right? All we've done is said, we've got a temperature hot and a temperature low, and we're gonna put some sort of machine in the middle. That this is this converts heat to work, or if we go in work and converts to heat flow or something, and there's some machine, but we haven't gotten into what is happening inside of this machine. Well, we're gonna get to all that, and that's when we're gonna go into the details of the Carnot cycle. For right now, all you need to know is this is a theoretically perfect cycle. So a theoretically reversible cycle. Reversible is the technical word for it. So notice there's a couple things we can notice. I should redraw that picture actually. If we have like a heat source up here that heat comes from. So this is at some high temperature, hot temperature, and then when we're all done, the cold or the heat flows out to some cold place where we have a low temperature. Like this could be the temperature of the air in the room or something like that, where it goes, heat has to flow from hot to cold. Then we could imagine that we have 3 different machines, and the reason I'm drawing 3 machines will become apparent in a second. I want to use them to illustrate a principle. So the first machine is, these are all like heat to work machines. Okay. This one has an efficiency 8 to 1, this one has an efficiency 8 to 2, and this one has an efficiency 8 to 3. and there's heat flow. So like, I don't know which direction the heat is flowing. Depending on if you're putting work in or taking work out, it's flowing one way or the other. With pulling work out, it has to flow this way, but if we're dumping work in, we can drive it this way. So I'll just draw these double-ended arrows. And then I want to note that this one, here's how they're different. This one is irreversible, cannot be perfectly reversed. This one is reversible. It's theoretical, it's like a Carnot cycle. So this one could be a Carnot cycle. And this one is also reversible. But these two are different because they're using different methods. So this one, I'm going to call method A, and this one is method B. So both of them are perfect cycles. They're theoretical cycles, which are totally reversible, but they are using different methods. So imagine that the nuts and bolts inside each machine are working differently, okay? One of them might be a Carnot cycle. That's one of the imagined reversible cycles. There are two principles at work here. I'll write it down here. Two principles that we can notice. Number one, and this is all obvious stuff, it's not deep. The efficiency of the irreversible cycle will always be less than the efficiency of the reversible cycle, right? Any non-perfect cycle is less than a perfect cycle. Hopefully that's obvious. So the first principle is that eta 1 is less than eta 2. The second principle to notice is that if this cycle is perfect, you can't get any better than perfect. And in fact, you can't get any different than perfect. Perfect is perfect. So this eta 2 is going to be equal to this eta 3. Another way of saying this is that it doesn't matter what the nuts and bolts are. It doesn't matter what method we're using, method A, B. If both cycles are reversible, if both are perfect, then they're going to have the same efficiency to them. So that's the second principle. Eta 2 is equal to eta 3. And these two things are both fairly obvious, but they're just, if we write them down, it makes them more concrete, and they actually have a name. Because they're dealing with efficiencies of perfect cycles, and Carnot, who was the one to come up with a perfect cycle, he realized these principles. I'm spelling things wrong. So they're called Carnot principles. Okay? The last thing here, talking about the efficiency of a cycle that I want to mention is we need to answer this question. Does reversible or perfect, does that mean 100% efficient? Does reversible mean 100% efficient? Because we're using the word perfect. So does perfect means 100%, right? Well, let's just do the calculation and let's find out. So you remember that eta, the shortcut I use to define the formula for eta is we have the energy out over the energy in. And for a heat to work engine, the energy out was the work, and the energy in was however much heat came in. And the work could simply be written as the difference in heats, so Q in minus Q out over Q in, which simplifies to 1 minus Q out over Q in. This is just a review. I've done this exact same thing up on the board before and showed you that formula. So you should be familiar with that. Remember that this is for any cycle. I'll actually write that down below. So continuing, I want to write this in terms of the temperatures. You'll see why in a second. That will be how we can answer this question. And so my conversion factor, if I have it in terms of heats, entropy, right? That's our formula, that S equals Q over T. So Q equals delta S times T. So let me just write this and you can see delta S out over T low. That's a way to write Q out. It's how much entropy is leaving the system. And then because the heat flowing out is flowing into the low reservoir, we write this as temperature low up here. And then delta S in over T hot. Okay, so hopefully this explains it to you. And this, so far we've not said that the cycle is perfect. So this is the case for any cycle. That's true. But we want to answer the question about a perfect cycle. So what is the definition of a perfect cycle? Remember, it's that the entropy generated, or the delta S, equals 0. So that means the delta S out equals delta S in. There's no change. However much comes in is also the amount that goes out. We're not gaining any entropy in a perfect cycle. So in this case, and this is now only true for perfect cycles. So let's write down eta for a perfect cycle. So it's 1 minus, and these are the same numbers, so they cancel. And I just get T low over T hot. So this is the special case for the efficiency of a cycle if it's perfect, like the Carnot cycle. This is sometimes called the Carnot efficiency equation because it defines the efficiency of any perfect cycle, including the most famous one, being Carnot. So this now can answer our question. If we want eta to be 100% or 1, then we already have 1. We want this whole thing to be 0. And that can be accomplished in 2 ways. So let's answer our question. Only if the temperature low equals 0, or temperature hot equals infinity. Because if we put infinity in the bottom, we would also get 0. And it doesn't mean that when you divide by infinity you get 0. There's a calculus way to prove that, having to do with limits. But those are the 2 ways that our efficiency can actually be 1. I love this definition because, or this realization, sorry, because this speaks to the fact that no real world system can have an efficiency of 100%. All I did to tell you that before was say that we were dealing with a super task. And I think that was a good explanation, but here is a way to see that. To get an infinitely hot temperature, well, that's impossible physically. You just can't do it. And also, if you remember way back when we talked about temperature, we had a scale. We marked this end as being absolute 0 temperature, and I said absolute 0 temperature is something you can never achieve. You can never get there. We can think of it, but it's not actually physically possible. And so this is in line with what we've just learned, that for some reason if we did get there and we actually had a temperature low of 0 degrees, then we could make a 100% perfectly efficient engine. So both of these things are impossible, and to try to do them would be like doing a super task. Okay? So don't get confused between 100% efficiency and the best possible cycle, or a reversible cycle. They don't mean the same thing. Reversible means the best efficiency. It doesn't mean 100% efficiency. Okay, so we're gonna hopefully do a lot of practice problems with this type of stuff and help cement it in your brains, because I realize that right now it's very abstract. Okay, so let's try to put some numbers to it soon. But for now, thanks.